I'm going to talk about motion-free imaging of vasculature and pigment by Lissajous scan polarization sensitive OCT, and I'm Yasuno from Computational Optics Group at the University of Tsukuba. In this talk, I'm going to introduce the fifth generation EMPATH imaging modality. The first generation of the EMPATH imaging would be the color fundus. Then we have invasive angiographies including FA and ICGA at the second generation. We also have the non-invasive versions of the angiography, such as FAF. And recently, we have another non-invasive angiography, OCTA. If OCTA is the fourth generation, what is the fifth? It might be a comprehensive, non-invasive, wide-field angiography. By using it, we might be able to assess the circulation, vasculature, tissue abnormality, and RPE abnormality. To establish this new angiography, we've been using two key technologies. The first one is the Jones matrix polarization sensitive OCT. By using it, we obtain pigment and flow contrast without invasiveness. The second one is the Lissajous scan OCT. It enables wide-field motion-free retinal imaging. Let me explain one by one. Although OCT and OCTA are useful, their field of views are significantly smaller than other EMPATH modalities, such as color fundus. It is mainly because of the relatively long measurement time. The OCT and OCTA images are significantly distorted by the eye motion during the long measurement time. Our trick to overcome this issue is the Lissajous scan. The Lissajous scan OCT scans the retina with a dynamic trajectory, starting from a diagonal line. It becomes an ellipse, and a circle becomes the ellipse again, but to the orthogonal direction to the previous ellipse. Then becomes a line again, an ellipse, a circle, an ellipse, and comes to the original line. This pattern is repeated several times and covers a certain area of the retina. The Lissajous pattern is particularly useful because each pair of segments of Lissajous cycle has 4 overlapping regions. These regions can be used as landmarks to co-register the segments. By this co-registration, we can perfectly and three-dimensionally cancel the eye motion. Thanks to the Lissajous scan, now we can have perfectly motion-free OCTA. Here is a case of BRVO. As you may see, fine vasculatures are revealed without motion artifacts. The same subject was scanned by a raster scan, but due to the severe eye motion, the OCTA was nearly unrecognizable. So, the motion-free Lissajous OCT is promising. However, its field of view is still up to 3 to 4 mm. We've been introduced a new trick to extend the field of view of the Lissajous scan. Here, as performing the Lissajous scan multiple times, we simultaneously slowly drift the center of the scan. We denote this scan as the Convolutional Lissajous scan. In our particular implementation, the elementary Lissajous scan covers 3 × 3 mm region. As doing this narrow field Lissajous scan, the center of the Lissajous pattern slowly drifts along a circle. Here, the diameter of the circle is 1.9 mm. This convolutional Lissajous scan finally covers more than 6.8 mm diameter field on the retina with the high density of the A scans. The acquisition time is relatively long as 42 seconds, but it is not really psychologically long for the patients. During the measurement, the patient is instructed to be relaxed and he doesn't need to really fixate his eye. Even he can blink. All the distortions occurred by the eye motion and the data missing by the blink are corrected by the post-processing. This convolutional Lissajous scan gives us a wide field OCT angiography with an 8.5 mm field of view. By comparing it with the color fundus, we find perfect matching of the blood vessel patterns. By segmenting the superficial layer, nerve fiber bundles becomes clearly visible in the OCT. In the OCTA, fine capillaries are visible. At the fovea, foveal avascular zone is also clearly presented. Owing to the three-dimensional motion correction, the en-face depth slice doesn't show any motion artifacts. Three-dimensional motion correction also enables motion-free cross-sections along any directions. As shown in this movie, the cross-sections are perfectly motion-free. Now we obtain wide-field motion-free OCT. The next point is how we obtain the specific contrast to the RPE and melanin. The key technology for this is the Jones matrix OCT. The Jones matrix OCT is a hardware extension of OCT, and it gives a three-dimensional distribution of the Jones matrix of the sample. The Jones matrix is purely mathematical and physical quantity, so it might be out of your interest, but it possesses full optical property of the sample. So, by applying proper operators to the Jones matrix, we can obtain several clinically useful contrasts, and it includes the flow contrast and the polarization uniformity, which is known to be sensitive to the melanin. By combining them, we obtain a pseudo-color image, so-called pigment-and-flow image. To generate the pigment-and-flow image, we used OCTA to define the pixel brightness. From polarization uniformity, we estimated the amount of melanin existing above each pixel of interest, and used it to determine the color of the pixel. In the combined volume, the blood vessel is appeared as red or yellow if there is no melanin on top. It's appeared as blue if there is melanin above it. So, in the normal eye, the retinal vessels appear as red to yellow, while the choroidal vessel appear as blue. By watching this volume from the top, we finally have the en-face pigment and flow image. Let me show some cases. The first case is an age-related macular degeneration. In the OCTA, we see the signature of abnormal blood vessel. In the pigment and flow image, this vasculature is appeared as yellow. It indicates the RPE about the blood vessel are damaged. This can be confirmed by a synthesized en-face RPE image that is generated by polarization-sensitive signal processing. Also in the polarization uniformity cross-section, the yellow melanin signature in the RPE has gone. The second case is a diabetic retinopathy. The wide-field OCTA exhibits hyper-scattering materials around the nerve fiber layer, and it corresponds to the whitish appearance in a color fundus. The pigment and flow image shows an orange color abnormal blood vessel close to the fovea. So, let me conclude my talk. Here we demonstrated totally motion-free wide field and mild contrast OCT. It can be used as the fifth generation of the en-face retinal imaging modality, and it will hopefully soon be translated to the clinic. Thank you for attention.